Welcome back to the Deep Dive. We take your sources, we dig in, and we pull out the knowledge nuggets you need. Today, we're exploring something really mind-bending, fractals, a concept that honestly changed how we see everything. Our mission here is to really unpack what fractals mean, how they show these patterns repeating everywhere, how they mess with our ideas about dimension and viewpoint, and the big picture philosophy from Benoît Mandelbrot about the real world.
It really is a fascinating journey. And Mandelbrot himself, he didn't just think of it as new math. He actually called it a new mathematical and philosophical synthesis, which is quite a statement. He saw fractals as this new geometry of nature, something specifically for dealing with all the messy, irregular, broken stuff out there, things that, regular geometry, Euclidean geometry just couldn't handle.
Things people just ignored before.
Pretty much, yeah. Scientists often dismiss these forms as like esoteric and unusable, just mathematical weirdness. But the amazing thing is these weird shapes, they actually help us understand the complex reality around us, the real messy world.
Okay, let's try and make this concrete. There's that classic thought experiment, right? The coastline one. How long is the coast of Brittany? Sounds super simple, like just get a map, measure it.
Exactly. Intuitively, you think it's got to have a length, a fixed number. But Mandelbrot showed really vividly that the answer you get depends entirely on how you measure it, on your scale. Think about it. Use a massive ruler, maybe kilometers long, you get one answer.
Okay.
But then use a smaller ruler, say meter-long steps. You follow the curves more closely, right? The length gets longer.
Right, because you're capturing more wiggles.
Precisely. Now imagine walking it, then a mouse walking it, following every pebble, then a fly navigating every grain of sand. The measured length just keeps going up and up. Theoretically, it could even go towards infinity.
Wow.
Yeah.
Infinity. That's hard to picture.
It is. And it really highlights that something like geographical length isn't purely objective. The scale you choose, the observer scale, it's an inevitable part of the definition. Your point of view literally changes the answer.
That makes sense. I remember reading Jean Perrin mention something similar way back in the Lysotome. He talked about how hard it is to define a tangent, like a straight line just touching the coast, because it's so jagged at every scale. A bit like Brownian motion, that jittery particle movement.
Exactly like that. It's the same kind of problem. And this leads straight into the idea of effective physical dimension, which sounds fancy, but it's actually quite practical. It's tied to the degree of resolution, basically. How closely are you looking? Think about a ball of yarn. Say it's 10 centimeters across, made of thread that's 1 millimeter thick.
Okay, got it. Ball of yarn.
Right. Now look at it from 10 meters away. What do you see?
Just a dot, probably.
Yeah.
A point. 0 dimensions.
Basically, yeah. 0 dimensional.
Yeah.
Now move closer. Say to 10 centimeters away.
That's definitely a ball. 3 dimensions.
Yep. 3-dimensional. But what if you could zoom right in, down to the 10 millimeter scale?
Then I'd see the individual threads, right? Like lines. 1 dimension.
1-dimensional threads, exactly. And then zoom in even more to 0.1 millimeters.
Then the threads themselves would look like little cylinders. So 3D again.
You got it. See, same object, but its effective dimension keeps changing 0D, 3D, 1D, 3D, again, just based on how closely you look. So it really makes you ask, if dimension isn't fixed, it depends on our perspective, what does that do to our whole understanding of reality, how we classify things?
That's a big shift, because dimension feels so fundamental. So if dimension shifts with viewpoint, what does this scale thing tell us about patterns? Does this lead to that idea of self-similarity, where things look kind of the same no matter how much you zoom in or out, repeating patterns?
That's the heart of it, yes. Self-similarity, where the parts look like the whole, just smaller. The classic math example is the von Koch curve or snowflake. You start with a line, add a triangular bump, then add smaller bumps onto those bumps, and so on forever.
Right, I've seen pictures of that. It gets infinitely crinkly.
Infinitely crinkly, exactly. And its dimension, it's not 1 like a line or 2 like a flat area. It's about 1.26.
1.26. A fractional dimension.
Yep.
A fractional dimension. It perfectly captures how wiggly or rough it is. It's more than a line, but it doesn't quite fill up a 2D space. It quantifies the irregularity.
Okay, that's weird but cool. But then you mentioned some curves, like the Pinot curve. They can have a whole number dimension, like 2. How can it be fractal if its dimension is just 2? Isn't that just a plane? Why is it still pathological?
That's a great question. Because it really pushes our intuition. Yes, the Pinot curve has a dimension of 2. It's a single continuous line, believe it or not. But it twists and turns so much that it literally covers every single point within a square. It fills the plane.
A line that fills a square. How does
It has infinite double points, places where it crosses itself. So even though its dimension number is an integer, 2, its structure is totally different from a smooth Euclidean plane. For fractals, the key is that the irregularity, the complexity, it's there at every scale you look. Zoom in, it's still complex in the same structured way. It blurs the lines between micro and macro. So yeah, dimension 2, but definitely not your average surface. Still fundamentally fractal in its nature.
Right, so it's about the structure of the irregularity, not just the dimension number itself.
Yeah.
Okay, but look, this is fascinating with curves and coastlines. But the source has really hammered home how this isn't just math theory. These fractal ideas pop up everywhere, in really unexpected places. It really starts to feel like this repeating pattern idea is fundamental. Can you give some examples?
Absolutely. And the range is just staggering. It really does suggest this deep interconnectedness, patterns echoing across scales. Okay, first, a surprising one. Telephone errors. Back in the day, data transmission. Mandelbrot looked at errors, and he found they weren't just random noise. They happened in bursts.
Bursts of errors, okay.
Yeah, and when he analyzed the timing of these bursts, the pattern looked just like something called Cantor dust.
Cantor dust, what's that look like?
Imagine a line. Cut out the middle third. Now you have 2 smaller lines. Cut the middle third out of each of those. Keep going, infinitely. What's left is this scattered, infinitely porous set of points, totally self-similar.
Ah, okay. Like dust sprinkled along the line.
Exactly. And the telephone errors followed this pattern over time. Not random, but statistically self-similar, with a fractal dimension between 0 and 1. The big idea here, what looks like random noise might actually have this hidden fractal structure. Changes how you think about errors, right? Not just noise, but structured bursts.
That's incredible. Finding order in transmission errors.
Yeah.
Okay, so if it's in data, what about like the physical Earth? Landscapes?
Good question. Yes, river basins and terrestrial relief. Think about river levels like the Nile. Sometimes they have these long periods of being high or low, way longer than you'd expect from pure randomness. They called it the Joseph effect. This can be modeled using something called fractional Brownian motion, basically random wiggliness with memory or persistence.
Okay.
And you can generalize this idea to model whole landscapes. Mountains, valleys, the resulting random surfaces have a fractal dimension that measures their roughness. For Earth's overall relief, it's estimated to be around d equals 2.3. So more complex than a smooth surface, d2, but not fully space-filling, d3. It captures that rugged, self-similar look that mountains and coastlines have.
Wow. So the very shape of the land has this fractal nature. And then, scaling up even more, galaxies.
Galaxies, too. For a long time, the assumption was the universe is smooth, uniform on large scales, matter spread out evenly. But observations, especially by de Vaucouleurs, suggest it's not like that at all. Galaxies seem to be clustered.
Clustered how?
Hierarchically. Clusters of galaxies, within larger clusters, within superclusters. If you look at bigger and bigger volumes of space, the average density actually goes down. This points to a fractal distribution, not uniform. The dimension seems to be way less than 3, maybe somewhere between 1 and 1.5.
Like a cosmic Cantor dust, but in 3D?
Sort of, yeah. A clumpy, sparse, self-similar structure. And get this fractal arrangement offers a neat solution to Olber's paradox.
Oh, why the night sky is dark.
Exactly. If the universe were infinite, uniform, and filled with stars, the whole sky should blaze with light. But it doesn't. In a fractal universe with lots of empty space structured in this way, most lines of sight would just miss the stars. They'd pass through the gaps.
That's elegant, a fractal solution to a cosmic puzzle. And Mandelbrot took this further, right? With his conditional cosmographic principle. What's the idea there? Sounds philosophical.
It is quite philosophical. It's a twist on the old cosmological principle that assumes uniformity everywhere. Mandelbrot suggested maybe the universe isn't uniform everywhere on the largest scales. Maybe it is fractal. But, he said, true observers, like us, living inside the matter, not floating in a void, would still perceive similar statistical laws about how matter is distributed around them. So you can have this non-uniform fractal universe without needing a special center or a privileged viewpoint. It respects the scalelessness of point of view on a cosmic scale.
Okay, that's deep. What about something notoriously messy, like turbulence, fluids swirling around? Can fractals handle that?
Mandelbrot thought so. He suggested defining turbulence not just by average flow, but by the shape of where the turbulence is actually happening. The support, he called it. He proposed this support isn't a simple volume, but a fractal set. Its dimension would be somewhere between 2 and 3, maybe around 2.5 typically.
2.5, so not filling all the space.
Exactly. That explains why turbulence is intermittent. It happens in intense, localized bursts and eddies, not smoothly everywhere. By saying the space turbulence occupies is fractal, you're fundamentally changing how you even define the phenomenon. You're embracing its inherent structured irregularity.
It's amazing how this applies from the cosmos down to, well, things we build.
Mm-hmm.
What about computers? The sources mentioned computer components.
Yeah, even in microchips and computer architecture, there's something called Rent's rule. It relates the number of external connections, or terminals, T, a module has, to the number of components, C, inside it. The formula is roughly T(a) times C to the power of P.
Okay.
Mandelbrot re-expressed this exponent P using a dimension D, like P equals 1 in D. Now, if the components are laid out flat on a plane, D is 2. If they're arranged in 3D space, D is 3. If they're linear, D is 1.
Makes sense.
But sometimes the measured exponent P gives you a D that isn't an integer, it's fractional. That's just the wiring, the connections, the very structure of the circuit itself is organized in a kind of fractal space. Maybe it's the most efficient way to pack things.
Even our own designs fall into these patterns. Wild. And beyond the physical, language, economics.
Absolutely. These abstract systems show it too. Linguistic and economic hierarchies. Take language. Zipf's law describes how word frequency works. A few words are super common, many are rare. This distribution can be linked to a fractal dimension. If the dimension D is less than 1, it implies potentially infinite unique words, and you can visualize it like a Cantor does. Lots of gaps representing the rare words.
So the structure of language itself is fractal.
Seems like it, yeah. And economics, too. Pareto's law, the 80-20 rule idea, how wealth or income is distributed very unevenly, that also follows a power law that corresponds to a fractal dimension, often around D2. So our communication, our societies, our economies, they exhibit these same kinds of self-similar, irregular hierarchical patterns we see in coastlines and galaxies.
Okay, pulling this all together, this idea of the scalelessness of point of view, it feels like the biggest takeaway. Fractals aren't just a math tool anymore. They seem like a whole new way of seeing reality, a different philosophy almost.
I think that's exactly right. Mandelbrot wasn't just measuring jaggedness. He was really arguing for a shift in thinking. He said, look, all this stuff mathematicians call pathology, these weird curves, no, that's not pathology. That's reality. That's the robust complexity of the real world. He wanted to fix the paradoxes of the concrete, where our simple models didn't match reality, by giving us better models, fractal models. It means accepting that dimension itself can be, pragmatic, even subjective, depending on your resolution, your viewpoint. It embraces the inherent irregularity, but finds order within it.
And it connects to how he went back and found those precursors, right?
Yeah.
People like Bachelier or Levy who had touched on these ideas earlier but got ignored.
Exactly. He actively sought them out. He felt understanding those overlooked ideas was good for the soul of the scientist. It's a reminder, isn't it, that real breakthroughs often mean challenging the status quo, being open to ideas that seem weird or non-rigorous at first. He showed that knowledge, even forgotten knowledge, is powerful when you understand it and apply it in a new way. He brought fractal geometry from the margins right into the center of how we describe nature.
This whole deep dive, it really hammers home that shift in perspective fractals offer. Finding this incredible, intricate order, these repeating patterns hidden inside what we used to just call chaos or noise. It shows that irregularity isn't just random. It has its own beautiful self-similar geometry, repeating at every single scale, everything connected.
Indeed. And it leaves you wondering, doesn't it? If fractals are truly woven into nature's fabric, coastlines, clouds, galaxies, rivers, maybe even our own thoughts in biology, and if they fundamentally challenge our neat boxes of dimension and order and randomness, well, how does that change how we understand complexity itself? In the world, and maybe even inside us, is chaos just a name for patterns we haven't recognized yet?
Something definitely to think about as you look at the world around you, maybe seeing those hidden patterns now. Thanks for joining us on this deep dive. Keep exploring, keep asking questions. We'll be back next time to unpack more.